Hello ChemComm. The last time we were together, we looked at some properties of matter, and today we're going to look at how matter goes through changes, both physical, chemical, and even nuclear. Let's get started. The most important thing that you have to remember when we start talking about chemical and physical changes is that the law of conservation of matter, or the law of conservation of mass, has to be maintained. What does that mean? It means that if we start with 50 grams of reactants, we're going to end with 50 grams of product. If those 50 grams go through a chemical reaction, they could be in different phases or states, but the same atoms that we start with have to be the same atoms that we end with. We cannot create or destroy matter. If you look down here in this graphic, you can see an example of a chemical reaction. We have calcium chloride and sodium sulfate, and they're mixing together in a closed container, and they're 300.23 grams before the reaction. After the reaction, we have new products, sodium chloride and calcium sulfate, but the exact same mass still exists. The same atoms still exist. They've just been rearranged into different molecules. Mass can be changed into energy, but that typically happens only in nuclear reactions, which we'll get to in a little bit. Here's just another quick graphic to show we have some atoms of element X, atoms of element Y. When they combine, those atoms all still exist. We've just created a different number of particles because they've bonded together. Let's start with chemical changes. A chemical change is a change that occurs when a new substance is made, or the composition, the chemical makeup or formula of that substance is changed into something new. Typically, these reactions have a very distinct visual change, and a lot of times they can be identified by knowing that it's hard to reverse them, or they're hard to go backwards. For instance, like we have a frying of an egg. It's really hard to unfry an egg. Or for instance, the rusting of a nail. If a nail rusts, in order to get that iron oxide, which is what rust is, back to just iron, there's more chemical reactions that would need to take place to get it back to just pure iron. Sometimes chemical changes can be a little tricky to identify. In the future slide here, we'll go through some ways that you can identify if a chemical change has taken place. Physical changes can also be a little tricky. Sometimes it can be obvious. If no new substance is made, then that means it's just a physical change. But sometimes it can appear like a new substance was created, even though it's the same chemical makeup as it was before. Let's take a look at some examples. This first one here can be very confusing. If you put sugar in water and stir it up, it's going to dissolve. And that could appear to be a new substance. The thing is, sugar and water mixed together is still just sugar and water, or salt and water, whatever solute and solvent you have. Dissolving is a physical change. It's just taking a solid and dissolving it into typically a liquid. Other things that are physical changes are phase changes. These tend to throw people off as well. But if water goes from ice to water vapor, it's still H2O. The chemical makeup is the same. We have not changed it chemically. And then finally, if you look down here at the bottom, we have a physical change, which is like the cutting of a log of wood, and then the chemical change is when we burn it. So any kind of like grinding or tearing, or like the rubber on the bottom of your shoes rubbing off, that would all be physical changes because it's still the same substance. Often when we have physical and chemical changes, a change in energy occurs, and they can be identified as either exothermic or endothermic. So with a physical change, typically we see this with phase changes. For instance, if we freeze H2O, in order to freeze water, we need heat to leave that water. That's why we put it in a freezer. So if heat is leaving, that means that freezing any substance would be exothermic. In the same way, if I want to melt ice, I add heat to it. And if heat is entering, if heat is being added, that would be endothermic. Endothermic, heat enters. Exothermic, heat exits. Make sure that you can apply exothermic and endothermic to physical changes, but also know how to apply them to chemical changes. When a chemical change occurs and it's exothermic, that means that heat is exiting the reaction, and typically we feel the heat. So when we burn things like a match or a log of wood or a firework, heat is leaving, and therefore heat is being, you can feel the heat in the surroundings. Endothermic chemical changes typically absorb heat from the surroundings. And so a cold pack is a good example of this. You twist and break the cold pack, and it starts absorbing heat from the surroundings like the pack itself. And what happens is you feel the surroundings as colder because heat's leaving the surroundings and going into the reaction. So you feel the surroundings, not the actual reaction, and that's why it feels colder. Okay, let's circle back to chemical changes here for a second. There are 4 ways to identify a chemical reaction. These do not always indicate a chemical reaction, but these are pretty good ways, or pretty good evidences that you can identify one. The first one is a color change. Think of the tarnishing of the Statue of Liberty or the burning of a match. The formation of a precipitate. A precipitate is what happens when you mix 2 solutions together and a solid forms and settles out. If we go back a couple slides, this picture right here is the formation of a precipitate. We're taking 2 solutions, mixing them together, and we're getting this yellow solid that's going to settle out over time. That's what a precipitate looks like. You'll see some of these in lab. Third, the production of heat and light. If heat and light are being given off, that's typically an indication of a chemical change. And finally, the production of a gas. If we're working with solutions, the gas you'll see will be in the form of bubbles. Something will start bubbling because it's bubbling through the solution, and that's a pretty good indication that a chemical change is occurring. Here's just a quick graphic showing some of the things we just talked about, some of the evidences we see with a chemical change. This is just another reminder. The law of conservation of mass has to be conserved. We can't start with a certain amount of substance and end with a different amount. And you might be thinking, but I know there's some chemical reactions that it seems like I have less than when I started. For instance, when you burn a log at a campfire, it seems like there's less there. The reason is because when you burn that log, you're producing CO2 and water vapor, and that CO2 and water vapor is going into the atmosphere. And so it's leaving, but it still exists. We didn't destroy matter, it just dissipated into the surrounding environment. If you look down here at the bottom, you can see that this is the formation of water with hydrogen and oxygen gas. So you can see we have 4 atoms of hydrogen and 2 atoms of oxygen, and they're bonded together in diatomic molecules. And when the chemical reaction occurs, we still have the same amount of hydrogen atoms and oxygen atoms. We've just chemically rearranged them. The law of conservation of mass still is held. The last type of change that we're going to talk about briefly, and we'll talk about more later in the semester, is a nuclear change. In a nuclear change, the nucleus of an atom changes. It either breaks apart or 2 nuclei come together. So those are pretty much the 2 ways that a nuclear change can occur. If 2 nuclei fuse together, we call that nuclear fusion. And if a nuclei breaks apart or fissures apart, we call that nuclear fission. Typically when this happens, new elements would be created. So for instance, if you had uranium ore and it went through nuclear decay, the new element that you would produce after that nuclear decay took place would be thorium. We'll go more in depth with nuclear changes later on in the semester, but for right now, that's pretty much all you need to know. This next part here is us just kind of walking through how we represent these chemical changes. Eventually, we're going to build to equations that explain a chemical change. But for right now, we just need to kind of lay some groundwork. One way to think about representing these chemical reactions is through the idea of letters, words, and sentences. In the English language, we have letters that we put together to form words, which have meaning, and then we use those words and string them together to form sentences, which tell stories about what's happening. In the same way, chemists use symbols to tell the story of what is occurring in a chemical reaction. At the most basic level, letters, we have chemical symbols. These are found on the periodic table, and typically they correlate with the name of the element. So for instance, nitrogen, the symbol or the letter is just a capital N. If you look though, there are some elements that have symbols that don't make sense. For instance, if you look at the symbol for lead, it's Pb. That Pb is coming from the Latin root word, which is plumbum. And tin is Sn, which is coming from stannum, and so on. So in most cases, the symbol is going to correlate to the name of the element. But in some, because they're based on the Latin root name, they'll be a little different. The first letter of every symbol will always be a capital letter, and then if there is a second letter, it will be lowercase. That is the correct way to write a chemical symbol. So just like we have 26 letters in the alphabet to help us make words, there are 118 symbols in the chemistry alphabet that helps us explain the chemical reactions that are occurring. And these are all found on the periodic table. So now that we have our letters, our symbols, we can start putting them together to form words or chemical formulas. Most elements aren't found by themselves in nature. They're unstable in this way, and so they want to bond with something else. And a lot of times the ratio that they bond in is based off their atomic structure. So for instance, if you were going to combine hydrogen and oxygen, it's just not one hydrogen and one oxygen. They actually bond together with two hydrogens for every one oxygen, making H2O. So the way we deal with that is we use something called a subscript to tell how many atoms are within that chemical formula. So H2O, the 2 is telling us there are 2 hydrogens in the formula. Here's a more complicated formula. This is sodium sulfate. You'll learn how to name these later. We have 2 sodium atoms because sodium is Na. You have 1 sulfur atom because there is no subscript after the S. We assume it to be 1. And then there are 4 oxygen atoms. So the subscripts really tell us the number of each atom in every compound. Now that we have the letters and the words, we can start putting them together in the form of a sentence or a chemical equation. We tell the reactants that we're starting with and then the products that we finish with. And we'd get something that looks like this. And we can do atom counts with these and make sure that we are fulfilling the law of conservation of mass. Notice we started with 1 carbon, 4 hydrogens, and 4 oxygens, and that's how many we're ending with on the product side. We'll deal more with chemical symbols, formulas, and chemical equations later on in this course. We're just trying to lay a little foundation at this point. Hopefully you learned a little bit about physical and chemical changes today, and maybe a little bit about how to represent them in the form of a chemical equation. Great job. We will see you soon.